Hi, my name is Gary Schnell, and I'd like to welcome you once again into my home near Milwaukee, Wisconsin. I am putting together a number of YouTube videos to highlight different areas of my book entitled Consciousness, All in One and One in All. This particular YouTube video will be on chapter 5 of my book, A Brief Introduction into Quantum Physics. I hope my whiteboard shows up, but if it doesn't, well, we'll have some problems. Back in the 1800s, there was this fella named Thomas Young. And he decided he would like to aim a light source at a double slit. You can see the slits here and here. And behind the slit, he had a film plate. Now, for the sake of the illustration that I'm doing here regarding quantum physics, I'm going to ask you to consider that this film plate is infinitely long, though it's not physically possible, but it will illustrate the ideas that I'm trying to get across. So he shined the light source on the double slit board, and you'd expect to get a concentration of the light being collapsed onto the film at the two spots that correspond with the slits. But that was not what we got. What we got is number 2 here. And I know I had to fit a lot on this board, so please forgive me. I'll explain it to the best of my ability. What he got was a number of hits. The most concentrated number of hits were in the middle, and then there was, fewer hits, and then there was a less concentrated number of hits, fewer hits, less concentrated, fewer hits, less concentrated, fewer hits, less concentrated, all the way on out, if we consider this as an infinite plate. And the same on this side. Fewer hits, more, fewer hits, more, fewer hits, more, ad infinitum. So what this looked like was that there was a wave involved, or 2 waves coming through each slit, so that the waves would interfere with each other, and there would be peaks and troughs, peaks and troughs, peaks and troughs, peaks and troughs, like the ripples on a pond. So we've got a couple ideas, or at least right now we've got one idea regarding quantum physics that comes out of this. And that's that there is a complementary exchange of information. The photons that are given off by the light source are collapsed into another form of information on the photographic plate. So it's a complementary form of information. A wave from the light source to a particle on the plate. Now, we have another principle here, that there is no predicting on what spot one of these light waves will be collapsed into a particle. Could be anywhere along this, and this is what we see with the bell-shaped curve. It's most likely to be in these areas where there are the concentrations, but it can go all the way out, all the way out. So there's an uncertainty here. And we'll get to the uncertainty a little bit more in just a second. Because as we go all the way out, and I mean this red line on this bell-shaped curve never quite touches the black line, never quite touches 0. So that way out here, these waves are being collapsed into particles. And way out here is not local from the light source. It's non-local. This is the principle of non-locality. So we have complementarity, uncertainty, Heisenberg uncertainty principles, and non-locality. Now, it's the non-locality that really explains the uncertainty. You can't predict where it's going to be. It's non-local. Now, this is most significant as we talk about quantum physics. There seems to be a space called non-local space, and we'll talk about that because there's a non-locality to this bell-shaped curve. Now, we moved down, and there was another step that was done. He didn't have a photon counter back then. We have them now. So he either blocked this slit, or he put a piece of film here where the light particles would be collapsed, and the other slit was left open. So what he got was fairly predictable. He got a concentration of collapsed particles on the photographic plate right here. Now, more recently, we've been able to modify these experiments such that we can pass one photon at a time through the slits. Now, that seems rather odd. What you'd expect to get is up here, because only one photon is going through at a time, so you'd get a concentration. You'd get a concentration of photons corresponding to the slits. But what we get instead, passing one photon at a time through, is we get this uncertainty and non-locality because it's a wave. And each photon goes through the slit as a wave, and it interferes with itself. A wave coming through here and a wave coming through here as the photon, and it interferes with itself such that we get this kind of bell-shaped spread. So here we have at least three of the principles of quantum physics. We have complementarity of information, of shared information. We have uncertainty, and we have non-locality. And this is what Young was looking at, and we've been able to do this one photon at a time experiment with more modern equipment, using things like interferometers and mirrors. We can tweak these experiments in any number of ways, and each way we tweak it is consistent with the nature of a photon as a wave and a particle. A wave, non-local wave, generating anything along the infinite magnetic, along the infinite photographic plate, and a particle that is very local, right there or right there or right there. So we have a movement of non-local becoming local. Now, the fourth principle of quantum physics is something called entanglement. Now, entanglement can be inferred from what we've talked about so far. It is where two photons or two electrons that have a spin and a spin and a mass, that we can make them very intimately involved with each other, such that they share information. And then when we let these photons go off in different directions, we can measure this photon out here. And once we measure this photon out here, let's consider that this photon over here is non-local. Once we measure this, we know the answer to this. So if we find that this has a certain spin, like a negative spin, we'll know that this has a positive spin immediately without knowing it. And the idea has been that it's because they were so intimately connected. Now, I would suggest that these rules that we're talking about that suggest non-locality, complementarity, and uncertainty, that they play a part in entanglement, such that we have this non-local space where where the waves exist, and so this photon is here and this photon is here, but they have waves. They're not collapsed at this point, so that when this one becomes collapsed, the wave in non-local space can immediately communicate with the photon that hasn't been collapsed, and then we know what this photon is all about. That would be something that I would suggest. I don't know that that's something that many in the scientific community would agree with, but that would be a way I would consider it. Now, in talking about this non-local space where waves of information exist before they become collapsed into local space of particles and what we see in space-time, there is this non-local space, and it's otherwise known as the zero-point field. It's known as the Akashic field. It's known as the implicate order. It has a number of names. I haven't even listed all of them at this point. And it's out of this field, out of this zero-point energy field, that we get the four particles of force. They would include the strong field made up of quarks, the weak field made up of alpha particles, the electromagnetic field made up of electrons, and the gravity field made up of what we speculate are gravitons, but we haven't found a graviton yet. So the four fields of nature, the four main particles of the four particles of nature, they arise out of this non-local space. Now we know that with this non-local space there is no absolute nothingness. Absolute nothingness would violate the Heisenberg uncertainty principle. And we also know that there is an awful lot of energy in this non-local space, an amount of energy that far exceeds the energy in our universe, that likely explains why our universe continues to expand, that likely explains why our universe expanded so rapidly just after the Big Bang. And we know that this energy exists because there are particles that come into and out of existence very, very, very briefly. We call them virtual particles, not because they're not real, but because they exist so briefly in space-time. And we know they exist because we've done an experiment, and we call the results of this experiment the Casimir Effect. And what is done is two pieces of foil are placed in a vacuum. So there's nothing else in this vacuum. And what's observed is that these two pieces of foil, they get closer and closer to one another. And there are two ways of looking at this. One way of looking at it is that the pieces of foil are getting closer because there's so many more virtual particles outside the pieces of foil than there are inside the pieces of foil, so these virtual particles push them together. The other way of looking at it is that these virtual particles are akin to strings, consistent with what we call string theory. And these strings have different sizes per the molecule that they represent. And these strings then, some of the bigger size strings can't fit between the two pieces of foil, but all of the smaller sized loops of string can fit between the two pieces of foil, so that there is an inward push of the pieces of foil caused by the bigger strings on the outside that can't fit on the inside. So this is called the Casimir Effect. Now, there's a most significant issue that we need to address as a result of quantum physics, and that's that when we do this experiment that Thomas Young did, or when we measure any wave and collapse it into a particle, that we are making a measurement of this particle. And there's a lot of differences of opinion that we'll get into in subsequent chapters that have to do with what it means to make a measurement, what it means to do an observation. But the thing I want to drive home right now is that when there is a measurement made, there is much more going on than the existence of this wave or the existence of this particle. The measurement involves a relationship between the person or whatever, squirrel, my truck, whatever it is that's causing the collapse of a photon or an electron. Whatever's causing that collapse, there's a relationship between what's being measured and the bits of information that we're talking about here. Now, information can't give itself meaning. It requires consciousness to have meaning. So what I'm suggesting here is that information and consciousness are very much intertwined, very much connected to one another. And we will talk about this more in a subsequent chapter, chapter 8, entitled The Intimate Dance of the A-Causal Cause, where I talk very much about the connection between consciousness and information. But it's important to be clear that this relationship exists, and this is a quantum shift, a paradigm shift of quantum proportions, whereby we're not just considering particles anymore or waves, we're considering the measurement and the measurer of these waves in such a way that there is a collapse and a relationship. And it's kind of like these particles, they represent the semantics of language, or they represent the hard drive of a computer, or they represent, what's another example? I can't think of another example at this point. But we have particles that represent a hard drive and the rules of language. But there is no meaning until we talk about the syntax of language. You can't get the syntax of language from the semantics. They talk about, monkeys typing out on a computer, and the chances. What are the chances of them typing out a sonnet? If they type forever. Well, it's so hard to get syntax from semantics. It's impossible to get syntax from semantics, is what I'm suggesting. This is the paradigm shift. Just like the hard drive has no meaning until we include software along with the hard drive. And just like the rules of language have no meaning until we write a poem or until we write a novel. So this would, we've talked about quantum physics, and I think it's also worth considering that this changes the game. It involves a relationship, and this relationship is a paradigm shift. So we have the 4 principles of quantum physics. They give rise to the 4 laws of nature and the particles that are the driving force behind these laws of nature. And we understand that these particles come from non-local space. So I hope you've enjoyed this presentation. If you have questions or concerns, please feel free to include them after the video. Please feel free to follow the videos, subscribe if you might. But otherwise, I hope you can take care and be well, stay healthy. Thank you very much.